The trick with PET is we already have the installed base of the equipment everywhere that can use it. It performs pretty well at the job it does. It's certainly, if you want to look at it from a material science perspective, the melting point is very low compared to glass and even pretty low compared to aluminum. So just the energy it takes to make it is already on a different footprint altogether. Um, since you can recycle it, and the cool thing about recycling it is you can do what we call SSP, solid state polymerization, which means you bring the polymer back to the length that it was when you wanted to use it in the first place. So a lot of polymers are damaged in the process of making something. And then if you try to recycle them, it's hard to get them the way you want. Like the polymer is always too short. In PET, you don't have that problem. So because of that, it kind of becomes a magic material for sustainability.
Welcome to the Matter Stack. This is a podcast that's engaging some of the brightest minds in the world of making physical stuff at scale, specifically chemical engineers, chemists, and other scientists that are reworking the chemicals and materials industry, taking this massive industry that's been built on extractive fossil-based processes and reimagining it in circular, sustainable, and better performing ways. This started out as a series of interviews that was internal to the company Origin Materials. I'm Ryan Smith, and I'm one of the founders of Origin. And over the company's life, we've employed and worked with some absolute world-class experts in chemicals R&D, material science, and process engineering. And so recently, we started interviewing them. What makes someone best in class at what they do? What is the right way to think about the technology stack of turning atoms into products? What are the implications of changing the industrial base from a fossil extractive source to a biological circular source? What kind of opportunities does it open up? And then once you have an idea, how do you go from milligrams to megatons? These are all questions we are hitting head on, both in practice and now in conversation. We've structured these conversations as podcast interviews, and initially, as I said, we just released them internally to the company to help share the insights across our team. But now we think it's time to share them more broadly, to start making them public. What's my goal in doing that? Well, the chemicals materials industry that was built over the last 2 centuries was built in a very particular way to take advantage of fossil-based feedstocks, oil and gas. And this massive industry that underpins the entire economy of physical stuff, clothing, automotive, building materials, packaging, etc., all the stuff that we're used to, it sits on a technology stack that is starting to be fundamentally redesigned and rebuilt. My goal in bringing these conversations public is to spotlight those layers of technology, what I call the matter stack, and describe how they're being redefined and rebuilt, both at Origin Materials and beyond. In this first to be released episode, my co-host Colin Shoemaker, a technology and economics director at Origin Materials, and I sit down with Jay Hanan. Jay, who is a senior R&D director at Origin, is also a world expert in polymer-based product design. His deep expertise extends from the fundamental chemistry and physics of polymers all the way out to the mechanical systems that are used to shape those polymers into products. And as you'll hear, he's absolutely best in class at every technical step in between. So without further ado, here is Jay Hanan. Today, we are joined by Jay Hanan, who we are excited to sit down with and have a discussion. Jay has a fascinating background and experience set and is doing really interesting stuff today. So, Jay, I think what would be great is if you could just start us off with sort of, paint the picture for us a little bit about who you are, where you've come from, and we can get into some of your current and even some of your future work. But if you can give us a little bit of your background, I think that'll be just to let folks know sort of where you are today and what you're focused on.
Sure, okay.
Maybe we can start there. You're at Origin Materials. You lead some of our key projects there, and so maybe if you could start just with that profile, just sort of situate yourself in your current work, and then I do want to retrace some of that history.
Okay, yeah, sure. So I'm a senior technical director at Origin Materials, but I'm also, especially it's important that I don't forget that I have a role at Oklahoma State University as well. I'm part-time on purpose. I chose to reduce my appointment there to allow me to spend the time that we're spending here with Origin. And at Oklahoma State, I'm in the mechanical and aerospace engineering department. and specifically, we launched a material science program there in Tulsa. So I'm part of helping that happen too. But here at Origin, the focus is on also materials, as I'm a material scientist. But specifically, we're working on materials that help improve sustainability. So that's kind of the general theme with a focus recently on PET. And we saw an opportunity, I guess we'll get into it later, to do some special things with PET together. So maybe that's what you're looking for.
That's helpful. What's the how'd you get into material science? Can we talk a little bit about that path? I've heard you tell pieces of that story. I'd like to understand, if we could, what
Yeah,
got you down that road.
yeah. There's short versions and long versions, but and I can remember when I first learned what material science was, uh, and it was new to me. So I can kind of remember how it's new to everybody else. You don't go necessarily to certainly high school or undergrad and take a lot of material science courses. Sometimes there's maybe one material science course for an engineering program, but in graduate programs you can find it. But the easy way of explaining it is it's kind of like mixing chemistry and physics together for solids. So it's the chemistry and physics of solids is what an easy way. Now I'm probably offending some material scientists out there, but we do need to understand phase changes and you know if some what percent crystallinity, for example, in these semi-crystalline polymers would be sort of the physics of that polymer, for example.
Yeah, I like that definition. I think that's simplifying and useful. Often when I meet someone who's a material scientist, they're studying ceramics or metals, or I actually surprisingly don't meet a bunch of material scientists who are studying polymer. You see polymer science people and you see
Right.
people that are in the plastics industry, but they don't necessarily have the material science background that you're describing. So how did you start with material science and then end up working towards uh, working inside the world of plastics? How did
Oh,
that happen?
sure. That was fun actually. So I double majored in chemistry and physics in undergrad, and coming out of that, got an internship in the plastics world. Let's say for a company called Reed Plastics in the '90s. I won't be specific, but back then, and really enjoyed it. That was in California, and it was. I took it for two reasons. It's funny. The guy who interviewed me said, "Don't do this again. Don't tell other people don't do this," because I told him I would only take the job if he would let me perform it in California, because I knew they had multiple locations. And he said, "You should never do that in an interview because it just makes you sound like you're not appreciative, of whatever they can give you." But I still know the guy that interviewed. He's a friend of mine that hired me back then, and we ended up working together later. But uh, anyway, that took me to California to prepare for grad school. Is really what I was aiming for, where I was going to study material science and do exactly like you said. It was mostly metals and ceramics was what I was going to study. But over that summer, spending time at Reed Plastics, I met people, made friends, learned the industry, and started realizing, a lot of the opportunity that was there, to the extent that they wanted me to stay. And it's not a typical internship in the fact that I was able to finish my undergrad in April, and my graduate school didn't start till September. So I had a few extra weeks longer than you would normally have to be there. And by the end of it, they were flying me around the country, setting up quality control systems for the company, um, as if I was going to work for I was in the quality department. I was going to work for the quality department. That's what they wanted me to do. But I think they didn't realize, and a lot of students today don't realize that grad school for engineers is often paid for. It's the government will have a contract with a professor or something, and that will pay for your tuition and even a little bit of your room and board while you're in grad school. It's hard to turn that down, especially if it's a good school. So I told them I can't stay. I have to go. I'm going to go do this. There's pieces to that story too, but already being seated with plastics on the time I was beginning my master's program at Caltech was where that began.
That's interesting. So it just gave you an exposure to it. And what about it? What about it did you like? Or maybe what did your master's focus on? How did you? We don't have to sort of dwell on that a bunch, but it'd be interesting to sort of know. I'm just really curious, like, because you bring a particular skill set to this industry that isn't. It's not a common path, right? It's not a common career path. And so I am kind of interested in sort of like, what is it about plastics that hooked you? And then how did you pursue that through grad school and into industry?
Yeah, there's lots of pieces to that. I mean, I remember people talking about residual stress and polycarbonate and not understanding it. I got to see one of the early PET lines in Arizona making bottles there. It was so slow compared to what we do now. But anyway, they were making new caps and valves, and there was actually an owner that had designed that was there at Reed Plastic. So little pieces of this connect to my present. But the what I worked on for my master's, it was funny because I tried. There are people, I learned this that summer. There are people that can taste water and tell you who made it. Like this is Sparklets or this is, Nestle or whatever. They can just taste it and tell you which brand it is. And I thought, boy, that's interesting. How does that work? It's kind of like wine. You can taste wine and know, what kind it is, how old it is, so forth. So there was a person, it was a faculty member at Caltech who was working on Project Sierra, he called it, where we could measure with his sensor cheese or wine or whatever. And I said, well, let's use it to measure if water is good or bad. Because knowing that was, there was no other sensor out there that could tell you, and it would be useful to make less scrap if you could know if the water was good or bad. And typically it was bad because somebody did something to the bottle more likely than the water. Like they would burn some plastic, create a scent that you could smell, and then you'd want to reject that water. So I tried to make this connection as like a first year grad student with the professor, and I don't think he understood the opportunity. This huge industry, nice new tool. Let's put the two together and make something happen. He didn't get it, and that went nowhere. And so, once one, attempt in a long string of failures throughout the rest of my life, where I would try to make these things happen. There's some that succeed and some that fail. You learn from both. But what I kept doing, you have to pick your faculty advisor. I did that, and in the course of doing that, you end up narrowing down what you're going to study for your master's thesis and then later your PhD. And I wasn't really particular on what I wanted to study. I told him I didn't mind which material it was. What I really wanted to do was learn techniques, like analysis techniques, measurement techniques, experimental techniques. So he took that to heart, like listened to me. It's funny, people come back to me and say, "You said this," I'm saying that, but it ends up being some, bookmark that makes things happen. So in the course of doing that, I worked on many different material systems, but my master's was on nickel spinel, the reduction of nickel spinel at about 2000 C in a carbon monoxide atmosphere. You could get it to create a composite. So you're reducing the spinel, so you're creating nickel metal inside of the ceramic. And the idea was the residual stress of that change in lattice would be favorable to make some kind of toughened ceramic. Just seeing if we could do it at all was part of the work that I did. And, I think I've got a paper from the late 90s on that if you wanted to look it up.
And you said that part of what you wanted to get out of this was to be able to sort of analyze and test and understand a bunch of different systems. Did that system in particular present a bunch of analytical challenges, or how did you? Because when it comes to analysis, you've got a bunch of tools in your toolbox. How did that happen? It sounds like that was a deliberate approach, but like, how did that shape the approach you took to grad school
That's
and
why
then
I was
where you
excited.
went?
Yeah, you're right. That's why I was excited. Urson Usendorf was my advisor, and he had come recently from Los Alamos. So he was there as a postdoc before he became a faculty member at Caltech. And so we were able to use his toolbox, which included neutron diffraction. So a lot of people never even heard neutrons could be used this way. They had something called a spallation source, which was relatively new back then, where you could spall off neutrons. They took care of all the physics, the thermal regulation, everything that needed to be done. But then you could put like sensors on the back end of all of this and use your material to diffract the neutrons. And if you know where they are, it's a time of flight measurement that you do with something called Rietveld analysis. Pretty intense stuff for the average person to follow. But you learn a lot of great physics, math, etc., material science doing that. We even explored something called Bragg edge technique with a new scientist there at Los Alamos, where you absorb the diffraction pattern rather than positively measure it. You're measuring what's removed by the material. So we tried a bunch of different techniques, explored this material, explored some other materials, and yeah, I got a lot of opportunities to use synchrotrons, neutrons, other lab techniques. We launched micro CT back then, was very new. So we were doing that again with a synchrotron radiation. So this is what I was doing in grad school.
So you got synchrotron, neutron, diffraction. How does that translate into the world of plastics where you ended up and spent a bunch of your career at?
Yeah,
Help me bridge those. They don't seem
sure.
related.
Well, people felt like they knew what happened in polymers, which is probably why you don't see very many people studying them today, because they felt like that was something that was well understood. Um, and one of the model systems might be to put a fiber inside of a polymer. And since it's clear, you can use optical imaging like interference techniques to see what's going on stress wise inside the polymer and at the interface between the reinforcement and the matrix that is the polymer. Um, was a relatively simple and already done experiment. The experiment that was not done was looking at, in my case, it was a silicon carbide fiber inside of a titanium matrix. And we basically wanted to do the same experiment where we look at the load transfer between the fiber and the matrix. But since we can't see that with visible light, we see it with X-rays. And you can actually treat the material itself as its own strain gauge if you know its lattice parameter and how the lattice parameter changes under load. So then that tells you the elastic strains that are involved. And you can even infer some plastic strains, and there's even other things you can do with watching grains and lots of things that you can do to understand mechanically what's going on inside the material. How does that connect to polymers? Well, one of the things that we had and still have, I think, I need to go check at Caltech, was the innovation and development of a new material called amorphous metals. So, and people, they sometimes call them metallic glass. And people that don't know what we're talking about might think, well, you're talking about a clear window made of metal. No, that's not what a metallic glass is. It's glassy because the molecular structure is random, like a glass is random. So material scientists, in fact, there's many words that we use in material science very precisely, like fatigue or stress or glass, that the rest of the world kind of abuses and uses in a bunch of different ways. When you talk about fatigue, you might talk about something else. But anyway, this amorphous metal allowed me to explore amorphous materials, which is really how I think of most polymers. And then, we could crystallize them and look at the relationship between being amorphous and being crystalline with these alloys, special alloys that were developed at Caltech. And it allowed me to think about and explore amorphous materials, let's say, in a way that maybe other material scientists that weren't exposed to that wouldn't have. And so I brought that back with me to polymers after I left. So I was all metals and ceramic matrix composites or metal matrix composites with ceramic reinforcement at Caltech. But after I left, I had maintained a relationship with the people that were in the plastics industry, and they would call me and ask me to help every once in a while with a problem they had. And so I'd bring this toolbox with me and say, all right, let's fix it this way.
So is that how, I guess you were talking about utilized metallic and ceramic materials. So I'm assuming that is how you found yourself at the Los Alamos National Lab. I did a little bit of data digging on you and on your background, and I just have to know about the jet propulsion stuff you did there. Is that
Yeah.
has to be more on the metal side, I'm guessing.
Well, now jet propulsion was different. So Los Alamos was mostly neutron diffraction, a little bit of X-ray, and it was certainly a special opportunity. I was technically a government employee, which was unusual. If you're a grad student and you can be a government employee at the same time, that's nice because you get paid like a government employee. So that's unusual. But yes, in 2000, I think it was, somebody heard about me through a friend and said, "Will you come help us at JPO?" And what am I going to say? I'm not going to say no. I was like, since I was a kid, I wanted to be an astronaut. Certainly, wanted to be involved with space and all this stuff. So what they needed though is they basically just needed somebody to help them solve problems. And what I was able to bring them that was maybe more valuable than material science at the time was we were coming up with new data analysis methods for the data coming from the X-ray methods. So I would get these two-dimensional images in inverse space, we call it, of the like all the diffraction information. So it's amorphous, crystalline, spatial, we call it uh, texture or orientation of the part is all represented in this inverse space. And analyzing that wasn't straightforward. There wasn't necessarily software that had that all figured out. So I was doing that with my peers there at Caltech. Well, they had a similar data problem at JPL. They didn't know necessarily how to avoid hitting rocks or driving off a cliff on the surface of Mars. And they had other problems too that were for the military. So I would bring the same data analysis techniques to the jet propulsion lab, and we solved some problems there for them.
That's fascinating how you're leveraging your skill set to multiple different industries. Because I think you went from rocket scientist to bottle maker, which is not a normal transition because you went straight to Niagara after that, right?
No, it was funny. I was at JPL for 4 years, is my recollection, and somebody handed me a job. It was somebody from Caltech that I knew. He was in he ran the TEM downstairs, and he said, "Here's this job opportunity at OSU." And I was, I think my second child had been born by that point. So they had, grandparents in Oklahoma. There was this job in Oklahoma, and you could basically take my resume and the job and like switch the titles, and my name could fit on what they wanted. So at a minimum, I've always told people this. At a minimum, it was a chance to go see my parents for free because they were going to fly me out to check out OSU. But I think it was the second day that I was there that I was already in. I didn't tell them this, but I'd already made up my mind. I'm going to apply. I'm going to, I guess you apply or they accept you, but when they invite you, you have a pretty good chance of them saying yes. So I was pretty much sold on the opportunity. I was going to get to build a new lab. I had built a lab at Caltech. I modified a lab at JPL, and I was going to get to build a whole new lab, two of them actually. So I had my Stillwater lab and a Tulsa lab at OSU, and for me that was a thrill. So that's where I went next, was Oklahoma. But anyway, I didn't stay there very long, as you noticed. It looks like I went straight into plastics.
Yeah, and I just speaking of plastic, I just pulled up on Google Patent. I put your name in, and I am still flipping through the pages of inventions that you've had in this area. A lot of them at Niagara, not all of them. And there's a lot here. So what prompted that? How'd you end up going to Niagara? And clearly you had a very productive tenure there. So I'd be interesting to understand what sort of how you approached it and what you were leveraging, that I'm still flipping through the pages of patents that you've put together.
So like I told you, there was a few cases where they had some leaks. Somebody I knew from Niagara that I'd worked with at Reed called me up in 2004. They had a problem. I was still at JPL. I came by and I showed them how a camera technology could solve that manufacturing problem, because we were using camera technologies obviously at JPL. And I didn't know this. I mean, I spent maybe a day there. They actually, like, another guy started a company based around what I gave him. I met him later. His name is Pat Phillips. But yeah, so, and he went on to have a successful career. But that was 2004. So I go off, I become a professor. I'm doing stuff still with NASA. And I think I did work for just about every government, like Army, Navy, Air Force, all of them. And the Marines are really special. I liked the project I did for them. But what ended up happening was
wait, what project did you do? I saw you're like smiling in that moment. Like what project did you do for the Marines?
So I've always, and I think every boy would admit this, found like armor very interesting, especially body armor. And there was an Institute for Protective Apparel Technology at OSU that I don't know how they heard about me, but we had a conversation, the director of that and me, early on, and they said, "Why don't you come help us?" I was like, "I'd be thrilled to help you." And so we started coming up with new body armor materials for that program. And I met some great people there. A lot of good things happened. And it's pretty relevant to why I went to Niagara, because we had everything set up, a nice program, lots of funding going to come to this program. And I don't know if you remember, I think it was John McCain and Bush and Obama all kind of got into an argument about the budget before Obama was elected president. And I think Bush was trying to do what he thought was the right thing and delay acceptance of the budget. And McCain was instrumental in not voting that budget through. And so when that happened, because we were a line item in the budget, we didn't get funded. And that killed that particular program. So I had to go look for another way. I had maybe 18 grad students working for me. I needed to fund this program, keep things going. So I had to find another way to fund it relatively quickly. I found another project through the Air Force. That project was accepted and approved on my end, but my industry partner pulled out last minute on that because they were upset for reasons I probably shouldn't describe. But I was now stressed in a couple of different directions of trying to find funding for my research team. And I was again, with this guy that had the problem I solved for him, a good friend of mine in the bottle industry. I met him for Christmas here in California. And um, I told him that I had this idea to make a nanocomposite that would solve a lot of their problems in polymers. So that was graphene was the key reinforcement material. And he liked the idea enough. He said, well, why don't you, um, tell me more about it, set up something. We can't fund you for 5 years, but we can fund you for a month. And I was like, a month is better than nothing. So we got started with that. And, it was month to month to month, supporting the team, growing the research, launching the innovations there. So that was a patent that came out of that I did at OSU, and that grew into a whole program. They had no R&D department. So as an external person, I started their R&D department. And I can remember them struggling over, is it okay for me to hire people to work for me at Niagara, even though I'm not an employee of Niagara, I'm an employee of OSU. So we had to work through how all that works out. And I took a sabbatical break basically from teaching, but then I learned how to kind of teach. I would come back and teach my course, even if I was supporting the launch of this intellectual property, because their base was in Ontario. So I had to go from Tulsa to Ontario to make that happen. And it just, I can tell you the obvious thing was when I got there and I started learning from their operators what their problems were, I could learn it through my eyes how to fix them. And so I would go and say, if you do these three things, you could, save money, make more product, and make your customer happy. And said, well, let's do that. And we just kept doing this. It was luckily the people I worked for, people that hired me there, trusted me to try those things. We did them, and it became the most successful, innovative package, at least for the water bottle industry ever.
And it's worth calling out because I think a lot of people who aren't in the industry don't recognize the name Niagara. They're like the largest, I think, bottler. There is almost all of the off-brand water bottle and other bottling.
They call it private brand.
Private brand. There you go. So it's they. My understanding is that the number of units they sell exceeds Pepsi, Coca-Cola, Nestle, like all of these brands that we're familiar with are exceeded by Niagara just through all of their private brands that they supply. Is that a fair characterization?
Yeah. When we started, I remember Nestle was the big guy and we were the little guy, like 4 or 5 plants. But now I think Niagara has something like 50 some odd plants. You're right, they're the big guy on the block now.
So I think what you're describing is the innovation that you and your team had inside of Niagara resulted in sort of packaging products that I've probably seen. What would I have seen or used that would have the J. Hanan imprint on it?
Yeah, it came in stages, and it wasn't just me, right? I had other good people there, but the I think it was called executive director of manufacturing had launched a new closure just before I arrived, and they were having trouble. They thought that if you added more material to the top of the preform, that you could lightweight the bottle because it would be stronger and have better top load. And what I realized was that was actually the wrong thing to do. You want to reduce the amount of material because it absorbs heat, and you need to keep the finish cold. You don't want to get the finish to get hot. So if you create this kind of gap between the finish and the rest of the bottle and you lightweight it, it creates all kinds of other opportunities for lightweighting too. And I did that first. That became one patent that was kind of the foundation for a lot of other lightweighting that led to different types of rib designs, cap designs, base designs for bottles. And so now when you go buy like a Costco water bottle or a Walmart water bottle, just about anybody, it's probably got a base that I designed. It's probably got ribs that I designed, probably has a finish and a cap that at least came from my team. We had good partners. We had, we worked with Cronus and Seidel and Husky and a lot of good partners in this process. So it wasn't like I did it on my own. But I do remember, they would send me a drawing. I would draw on it, how to fix it, and send it back. And that's the part we would make. That's kind of how this would go.
So you're the reason that all the water bottles have little ribs on them. I had no idea why water bottles ever had ribs on them.
Well, there were ribs before I got there, but the ribs were not optimal. They would lean too much. The bottles would start bending even in the pallet. And you'd have this whole pallet of just kind of leaning product, which is bad for the warehouse. So I came up with ways to strengthen it so it wouldn't lean. That was one of the early things I did.
So the ribs are providing enough structural integrity, but also what are less polymer, less weight.
If you optimize the process for for the PET, then you'll get a better product. So that includes optimizing the preform design for the bottle. A lot of people are a little too careful there. There's some guidelines that Husky published, for example, that makes it easier to inject. Well, I'm not selling preforms; I'm selling bottles, so I need to optimize for the process, not just for the injection machine. So they would kind of push back that you're going beyond our guidelines, but it turned out that that was the right thing to do for the whole system.
So for those who don't know, preform is it's what you make before you blow it into a bottle that would then be filled with a liquid. Yeah, there you go. Perfect. It's a little it's a little mini bottle where the walls are kind of thick, and then they blow it out like a balloon almost into a particular shape, and then that's what you actually end up filling, and consumers are familiar with. So in the course of doing that, though, there is this you're sort of pushing the materials, sort of the material's ability to the limits, right? Because you're lightweighting things, you're using less and less and less material, and you're sort of trying to find all the little spots inside of the design of the bottle that can still support its function, but sort of shaving off as much material as you possibly can. And all the while, you got to maintain sort of food contact compliance. It has to look have to look crystal clear and pretty. And you've got a highly constrained system. And you're trying to just shave pennies off of
Sure.
off of the cost of that thing.
But a billion pennies is worth something.
I believe it. Yeah, exactly. So I don't know. I think it's I'd be interested in like how your background with the sort of material science that we were talking about a few minutes ago sort of played into the approach that you took as you're really pushing the limits of what the material is capable of. Like I kind of feel like you just like took, like, you can't make that bottle thinner, right? Like you can't lightweight it more. You just took it to the absolute sort of plateau, the minimum of its capability. And so I'm wondering, was there a kind of perspective that you were bringing to that problem to make that happen?
Yeah, I think so. Part of it is also understanding the machine, right, and what its limitations are, and maybe understanding data analysis. So there's having worked in automation and machine vision, where I'd published some work, I knew what was capable there. Knowing how to do data analysis and look within the noise, I could kind of see, what the plant was teaching us too. And then, of course, they talk about the dog whisperer. So I'm kind of like the atom whisperer. I feel like I know what those atoms are doing, right, when they're organizing themselves, because I've been looking at them for so long using diffraction techniques. I knew what a crystal was. I knew what kind of this thermodynamics was that was going on inside of the materials. And when you put all three of those together, it made for a nice combination to say, well, where is optimum? Uh, and so you talk about shaving off pieces. You could do that, but you wanted to do it within the capability of all the equipment. So that was and I cannot take all the credit, right? Because the equipment that Niagara purchased was top of the line. And the plants that they run were clean and organized in a way that a lot of the competition didn't have. And so it was funny because we pushed the limit. It was like this little battle. Like they would be light, and then we'd be lighter, and then they'd try to go lighter, and we'd make sure we're lighter. But at some point, when they tried to go past us, they would make this terrible bottle that wouldn't even stand up.
Your comment reminds me of, sometimes you get a water bottle and you go to take the lid off of the tamper evidence band, and you end up just crushing, or like you just torque the bottle so much that the tamper evidence is stronger than the bottle itself. And so, that must be an evidence of maybe lightweighting gone too far, or maybe it's even the tamper evidence was too strong. I'm not sure.
You got to do the process right. I mean, even today, I can go look at a bottle and tell you if they're paying attention or not when they make it. So you've got to make it the right way, first of all.
So are you just, I'm trying to imagine, you're sort of balancing all these attributes, sort of what the machine can do, what the material can do, the requirements from a consumer perspective, environmental perspective, cost perspective. I'm wondering, just as you're optimizing all of that, was it ever the case that someone would come up with just a new innovation on a machine? And you're like, oh, that unlocks a whole other thing I've been wanting to do for a while. Like how did the sort of the innovation ratchet as new things became available?
Yeah, that's a good point. When Niagara became had more buying power, that would bring more people to come sell stuff to them. And so they bring their latest innovation in drying or base molding or whatever. There was some really neat things that I got to see people try to do. Some of them were practical, some of them weren't. And the ones that could work, especially in the space of vision and automation, there was a lot of opportunity to do better there. And I recommended that the company take advantage of it, and generally they did. So it, as far as I know, it's still paying off. It's funny. There's a human component to this too, right? I can remember one company that I won't name, whose leadership was just really, um, what's the right word? They weren't friendly, right? They weren't nice people. And even though their technology was useful, they were so proud of it and just so kind of grumpy that it made you not want to use it. You know, and because you got to have people you can work with, people you can develop with. So, so there was that, but also some aggressive companies out there that would try to steal ideas from others. I saw that happen.
Yeah, I bet. I bet. So you're through the course of this pushing the limits of PET specifically, and you're probably getting to know that material really, really well. And I know now working with you, I know you do. Uh, uh, as you know, people have mixed feelings about plastics and packaging and all of that. Um, but I think part of it, part of the solution is, finding something that's recyclable, finding something that can be sustainable from a carbon footprint standpoint, and I think PET has a lot of really unique features from a performance and mechanically, and also in terms of recyclability and potentially even for carbon footprint using the Origin technology. And so I'm wondering, either in the context of the bio low carbon PET work that you've done with Origin and Origin's doing, or maybe even just outside of that, how do you view PET's place in the world? And I'm kind of thinking things like monomaterial and sort of where the industry sort of talks about going. What's your perspective on that? How do what do you think PET specifically in the family of commodity polymers is going to be capable of doing?
There's a lot to that question, Ryan. What you made me remember was when I first heard about Origin Materials. I wasn't at Origin Materials. I heard about you, and it looked like a great opportunity. There were other people trying things. The problem was people were trying other polymers. Let's take PLA as an example. It was too brittle. The infrastructure wasn't there to support it. It didn't really biodegrade as well as people thought it might. So but people wanted to try something. They wanted to be more sustainable. And early on, people were even kind of afraid of recycling. So, let's say 2013, 14, whatever. Um, Recycling technology was kind of new, and people thought it was a little bit dirty. So they were scared to drink out of something that they weren't sure was clean. But the trick with PET is we already have the installed base of the equipment everywhere that can use it. It performs pretty well at the job it does. It's certainly, if you want to look at it from a material science perspective, the melting point is very low compared to glass, and even pretty low compared to aluminum. So just the energy it takes to make it is already on a different footprint altogether. Since you can recycle it, and the cool thing about recycling it is you can do what we call SSP, solid state polymerization, which means you bring the polymer back to the length that it was when you wanted to use it in the first place. So a lot of polymers are damaged in the process of making something. And then if you try to recycle them, it's hard to get them the way you want. Like the polymer is always too short. In PET, you don't have that problem. So because of that, it kind of becomes a magic material for sustainability. If you can get it back pretty much as clean as you can get back glass, but you don't need to, heat it ridiculously hot, melt it, everything's gone after you melt it. You can filter it, even in the melt. You can't, it's hard to do that with a lot of materials. And you don't have to line it with anything. Aluminum, you have to line with polymer anyway. Otherwise, it's going to get eaten through by whatever liquid you put in it. So you can really go monomaterial with PET. Eventually, I mean, speaking of monomaterial, that's an important goal. It would make recycling even easier. I don't want to discount the advantages that chemical recycling will have or advanced recycling will have, because I think that's an important area to continue to do research. But mechanical recycling already works. The technology is maturing and continues to mature. They can pull out and vacuum any unwanted, like if somebody puts they test it. They test putting the equivalent of gasoline in a plastic bottle, throwing it in the recycle bin, and making sure that it doesn't come out on the other side. So since that's already working, the fears that people had are gone. We should just do more of this.
So when you hear about, I mean, there was a recent study that showed that polyethylene was sort of absorbing a bunch of contaminants and things like that. PET really sidesteps a lot of that just because it's so amenable to these sort of cleanup steps.
Yeah, I mean, that's part of it. You have to dry PET to use it. And in the process of drying it, you push water out, but you can also push other stuff out if it happens to be there. Now, generally, it's not there because it's clean anyway, but there's water in the atmosphere. You know this. It's high. To use it, you have to dry it. You don't dry polyethylene. You don't dry some of the others. So that's an advantage as far as the cleanliness of PET is concerned.
I see a lot of people talking about, that are worried about plastics going back to glass. Uh, I mean, you talked about the sort of the heat, the process heat difference. That's pretty substantial, but there must be a lot of. I'm just thinking of things like performance attributes, like breakage and things that are a big deal. Any perspectives on that?
Yeah, breakage is an easy one, right? I mean, I've done that. You've. I was pushing my kid in a shopping cart, come around the corner, and I didn't know they had this display of wine bottles. Couldn't see it over the you have that stroller, like baby, carriage in the shopping cart. I couldn't see it. Ran right into the thing, knocked over I don't know how many wine bottles. It's embarrassing, but it's also wasteful that they break. Yeah, there's that. But glass is very impressive from a barrier perspective, and it will always be impressive from a barrier perspective. It's just, I just saw recently, I was at a material recovery facility. They had this problem where the people with either plastic or aluminum, they would leave the cap on the bottle for the glass and it gets crushed. They have to crush all the glass. And basically that cap gets mixed in together with glass. And so they don't want it. They set it up, they have to scrape, that becomes waste for recycling. You could probably make a long Pareto chart, figure out what the most important reason is why plastic is better than glass. There's certain things that you always will put in glass, but if you can put something in plastic, especially PET, and maybe even a PET that's modified for high barrier, that's always going to be the best choice.
So you talk about modifying it for high barrier, and I guess this kind of gets at a larger question. So as you think about taking a lot of the plastics that are out there, polyethylene or PVC or polystyrene, and look at their particular use, especially if it's getting thrown away, it's going to a landfill. It's like, oh, it could be recycled if it was PET, or at least it wouldn't degrade over time, like you're describing. What are some of the typical challenges that you encounter when you are taking something that's typically made out of, let's say, polyethylene or PVC, and saying, let's make this out of PET, right? So you want to use a more sustainable material. What are the issues that you run into? Because I think, and I'm excited to talk about more about sort of your current project where you are overcoming a bunch of those.
Yeah, a good example of that is in the milk business. So people have done a lot of work on making kind of small machines that'll extrude. It's a low density polyethylene, but your typical milk carton can be made of very small volumes, very cheaply, and you put fresh milk in it and get it in the store. It's a little bit harder today to make a PET bottle as cheap as that LDPE bottle for the small volume. Now, when you go to a reasonably high volume, like a 500 bottles a minute or 700 bottles a minute on a gallon sized bottle, now it's obvious that PET is going to win on the commercial side too, but not everybody's ready to go to that scale. So that's one of the reasons why it hasn't happened. There's this installed base of lower cost equipment that can run lower speed, that can run regionally what people need for their farm. Same thing is true of Tetra Pak. It can handle relatively small install base, relatively lower cost introductory to the economics. Over the whole picture, total life cycle, total cost of ownership, it's going to be worse. But if you need to get in and get started, that's one reason they're there. So maybe we as a world need to figure out how to make it easier for people to start out in PET. I don't know that the market wants that to happen. They probably like having their little worlds that they control. But
you're mentioning economies of scale, kind of, unlocking, PET. There has to be some kind of technical development that, they started out in whatever they chose, and now PET is able to, or some kind of functionality or technology for PET has allowed it to, perform better, as good or better. But now it's harder to restart the development machine. What is there some kind of development that happened, or?
Yeah, there is. There's some work on extrudable PET. there's a so people played around with additives for PET. So you're familiar with PETG and some of the other things. The problem is a lot of those weren't as easy to recycle. And so then they became punished and people had to circle back, away from those. There's opportunity. I mean, we're probably talking again about things that Origin should do in the future. So maybe we shouldn't go too far down this rabbit hole. But I've always said that the projects that we have, the ones that we're working on now, they're just the beginning. There's all kinds of opportunities to go help the farmer, to go help the person who doesn't know how to recycle, to go help the wine farmer. What do we call him? He owns a vineyard. Is there a special name for a wine farmer? I don't know. We can help all of these people do something more sustainable if we just unlock a few little recyclable tricks that I think we can do. First of all, with PEF and FDCA, but in general, just taking a quick look at.
So you mentioned a couple of things like PETG, PETF, stuff like that. Is PET just more prone or better suited to be tweaked and adjusted to a specific application than other plastics, or does that give it an inherent advantage?
I don't think it is necessarily. It's just that it's the guy in the room. It's the big guy. So there's other polyesters, right? There's other polymers, and maybe we could talk to Isaac or somebody who could give you a whole long list because that's what he does or he knows really well. But the trick is PET's there, and it's only going to get bigger, right? We've heard about Corpus Christi coming online relatively soon, the largest PET plant ever built. So we need to learn how to do that sustainably. That's just the logical next thing to do.
So I want to, and this will bridge a little bit into your current project for sure, but I want to ask you to, if you can, well, I know you can, take a bottle that we're used to seeing, and tell me sort of as we look at the components of that bottle, the label, the inks, the adhesive, the cap, what happens when those see a recycling center? How much of that can be made in PET or made in such a way that it's recyclable versus what parts of that aren't? What are the challenges that we faced with that particular product over the last decade, and which ones have we solved and which ones are we still trying to solve? How do we get to 100% recyclable?
If this ever does go public and there's a comment section, I'll be interested to hear the arguments against what I'm getting ready to tell you. but early on, lightweight bottles were not ideal for recycling. So the recyclers didn't want them. They liked the heavy, thick wall bottle because it's easy to chop up. You have, something, the aspect ratio of the flake is really a detail that they wanted in their favor. But that's improved. In fact, it's to the point now that I see more recycling of thermoformed trays and egg crates and things like this than I've ever seen before. And those are more available than they've ever been before. So we're already kind of walking down this march towards PET, but it's not a perfect march, right? There's contaminants along the way. So I have this bottle now in my hand that I got yesterday to help me think about it. But of the different components, the thickest parts are at the base, where around what we call the gate. It's relatively thick, so that's valuable to the recycler. And then the finish is generally a little bit thicker, the threads that are under the cap. And then all along the wall, then you've got relatively thin PET. If it's a hot fill bottle, they like it. If it's like one of these heavier bottles, they really like it. The light bottles, they're learning how to deal with it. They can deal with it now. What they don't get, though, if you notice on here, is this label. A lot of times the labels can be polypropylene or paper or waxed covered paper or something that would contaminate the recycle stream. And then, of course, there's the cap, right? And you can see this is a natural colored cap. It's HDPE. You can't recycle HDPE and make another cap. So that gets downcycled in the process.
And the label, how does that disrupt the recycling, or does it just go somewhere else?
So when they chop all this up into flake, they stick it in a water bath. Typically, there's other ways, but typically in a water bath, the PET sinks and the label on the cap floats. And so those get stirred together, chopped pieces of label with chopped pieces of cap. And like I said, if it's a polypropylene label, now you've got polypropylene mixed with polyethylene. There are research projects working on how to separate those, but it's not something commonly done. So you have this kind of waste stream of mixed polyolefins, they call it, that you can hot press that into a shingle or a floor tile or something, but you're not going to turn it back into a label or a cap.
it's not a true recycle. It's just getting downcycled. What's sort of the best, what's the state of the art or sort of the best solution around labels and adhesives and inks? Surely people are working
Yeah.
on this.
Well, I just learned a few months ago that what I thought was one of the best approaches they discontinued, as far as you could print a label on the bottle and
Yeah.
wash it off in the recycling process. So the company that was doing that, Gronis, I guess they weren't getting enough um, acceptance in the market for their technology. Now, I have some advice for them on how to do it better and faster. If they want to come talk to me, I think they can restart that program.
Of course.
But anyway, there's printing the label. Makes a lot of sense to me if it's a washable. And um, I mean, the cap, right? This is Origin, so we have our PET cap. So you put that on there, that solves the cap problem.
Yeah, so this is the question I always get when I talk about the CAP program that you're leading, where it is this idea of taking what was a at best downcycled material and replacing it with a fully recyclable PET closure on the top of the bottle. Uh, the question I always get is why wasn't this done 20 years ago? Why, what changed or what did you figure out that wasn't already knowable or known?
And 20 years ago, I guess I was in the industry, so I can kind of comment on that. First of all, nobody was thinking about recycling the same way back then. But it is true that I heard somebody tried to do it sometime around year 2000. I don't know all the details, but it didn't work. Then there was other attempts more recently. There's even an attempt to do it right now, different than the way we're doing it. It's interesting. But
I've also heard other attempts as well. There's sort of a holy grail quality to this project, right? People have been trying to crack this code for a while. So yeah, tell us what was unique about Origin's approach.
Do it from the way everybody's always done it before. You're limited to thinking the way you've done it before, and that's what they were doing. All these closures are either made one of two ways. They're injection molded. You can tell if it's injection molded, it has a little gate mark in the center of the cap. That's an injection molded closure. So if you have a closure that's flat on the top, it doesn't have that gate mark, it's compression molded. But either way, when these are made in the machine, you typically pop them out of the mold. So it's stripped from the mold. And the process of stripping polyethylene from the mold doesn't really damage it. It goes back to its original formed shape rather quickly. If you try to strip PET from a mold, that's the last thing it experiences. It's too the modulus is too high. You damage it permanently. It doesn't work. So people try to come up with tricks, go really short on the threads, maybe put a moving part inside the mold. They'll try some tricks to get it to work, but you need interference. You need negative draft, they call it, inside the mold to get a closure that interacts with a standard finish. So it doesn't work. But we came up with another way, the cap forming that I talked about in another video, or we can talk about it here. That does work.
How do you manage those expectations as, there's a tangible product on the horizon and, the company or whoever sees, great opportunity, great scale, great demand. How do you balance innovation and going to market successfully with the challenges of economics, demands of business case, and how do you balance those between your team?
Well, there's probably not a short answer to that question either. The hardest thing about, and maybe it's part of the barrier to entry for the rest of the world, to do something like a closure like this, doing it in the lab isn't good enough, right? You can do as much as you want in the lab and try to get as close as you can, and you're still not done because the plastic has a life in its it has a history, it has a thermal history, it has it matters how long it is between the time when you make it and the time when you trim it. It matters how long it is between the time you make it and the time you cap it. So those times are hard to get quite right in the lab, but that's what you try to do. You try on the small scale to discover what all the problems are, predict what all the problems will be, and fix them as much as you can before you go big. But then you also have to, I think, be very honest with the business people, your customers, or your executive leaders, et cetera, so that they see that this isn't easy, that you've got to find a partner that can tolerate a little bit of development. And what's wonderful, one of the many wonderful things about Origin is that we can tolerate the development time that it takes to go do something special that's never been done before. Maybe we're a little more sensitive to it than we used to be, but it's a special place where there's innovative people and innovation is kind of praised or sought after. And so it's almost too exciting to be a part of a group like that. Ryan and I think get too excited sometimes.
You have the motivation from the back end, the company you're working for, and to do that. What's the 3-point pitch that you take to a customer that would need to transition their entire facility or their entire process over to a new material? Is it do they need to be convinced? Are they knocking your doors down? What's your
I
perspective?
imagine that they get it as soon as I tell them it's a PET cap. I just imagine that their brain starts filing through, oh, this is going to make a lot of sense. And they start seeing it right away. But I'm also a little bit careful. We're trying to start with something that is, from their perspective, just change the material. You don't have to change the finish. You don't have to change the line. You don't have to change the rails. You're going from what used to be HDPE on a certain bottle to now it's PET. Long term, and I haven't had to explain this to a lot of customers yet, but I think we need to spend a little bit of time explaining it to them. There's an end game for this that is cost savings for them. So because it is PET on PET, we can take advantage of that and make something that's more efficient than has ever been made before. There's concessions being made to allow HDPE to interact with PET that we won't have to take. That's a longer development timeline, but the sophisticated customers should understand that there's a lot of value there and they don't want to be second to the line. They'd rather be first to the line to do that.
You talk about the sort of the balance between sort of the patience with new technology and innovation and the urgency to move something forward. Are there what's over this horizon? What's sort of the set of products or solutions that you're already thinking about or interested in? You talk about this team that you've been building, sort of bringing them forward as you describe sort of the next horizon to them. I'm sure. How do you describe it? What's it look like to you?
Yeah, there's a lot of pieces to that too. Certainly, just within the CAP framework, there's enough work to keep people busy for a decade, I would think. Just going in and helping every industry from medical to cleaning products do it better. So that's part of what's over the horizon. But like I said, when you go to the new material, you open the door for other kind of fun things to happen. So changing the cap will allow us to change the finish, which will probably change the bottle. It's going to change the ability to put wine in the bottle, for example, because you get better barrier than you've ever had before. So now let's think about doing wine in plastic or beer in plastic more so. They do it in Europe already, but not so much in the US. And so there's those opportunities in new products. But that is still kind of a small focused view. What if we look at other plastics that are in the package? Can we replace those too? I think the answer is yes, and maybe very efficient yes. The pallet, I mean, I did a project one time on redesigning the truck that the pallets are carried in. So, I mean, I look at this whole chain from beginning to end and see opportunity. We're leading the way, though. If we create more uses for monomaterial PET, we're going to create a purer PET stream that then creates other opportunities for recycled content in an automobile or recycled content in whatever. If we really go as an industry and stop using labels that contaminate the recycle stream, those technologies can be applied elsewhere too, and it becomes the demonstration or the leading edge platform for everybody else to be more sustainable. So that's now 2 decades out, right? And we're just gonna keep going from there.
So the name of our podcast is MatterStack, and that comes back to this idea that when you're basically making products out of matter, out of atoms. You mentioned you're the atom whisperer, right? So and you're talking about these layers in the technology stack that take a given material and new capabilities with equipment, new kinds of design thinking, new ways to move that material into products. And at Origin, we even start earlier in the stack than that, right? We tweak the material. We say, okay, well, here's your typical PET, but look, we can actually tweak it. We can tune its chemical composition in subtle ways that give it sort of different kinds of capabilities. And I'm wondering, what has it been like for you having that as a potential variable that you can use in the design thinking that you bring to these problems?
Oh yeah, it opens all kinds of. It allows you to take a risk that you wouldn't otherwise take. If you know that when you hit a wall, you've got another, orthogonal vector that you can pass to get around that barrier, whatever it might be. And, changing, knowing first of all what the material actually is useful, because a lot of people don't know what their PET really is, and then being able to modify it is also very useful. So I mentioned modifying it with graphene before, modifying it with PEF now, continuing that I don't want to say legacy, but chain of events makes a lot of sense to me.
Well, this has been good. It's been a fantastic conversation. I think we've gotten to know a lot more about you, about PET. You're kind of like the Michelangelo of PET. You're sort of making new stuff out of it. It's great. I love it. I think plastics have solved a tremendous number of problems in the world, and PET is particularly well suited to do that in a way that's sustainable. And you're helping make that possible. So that's exciting to hear how you think about it and your approach. But this has been fantastic.
Yeah,
Yeah,
we're only scratching the surface here, but there's a lot of opportunity. But anyway, thank you.
before we fully close out, I want to loop back to a more of an a personal question, which I like to ask people that I value their opinions or their technical prowess or whatever it may be, and to help people maybe identify what it is within themselves that could do something similar. Is what was one of the most impactful events that you have had in your life or career that's shaped you to who you are today, that's led you to be able to make these innovations to PET or innovations throughout multiple industries. What was something that was specifically impactful for you that kind of shaped you for who you are?
I don't think we understand ourselves as well as we thought we do. Think we do, first of all. So I don't know that I'll get this answer quite right, but I remember in my physics class seeing this picture of Cherenkov radiation or Cherenkov radiation. I want to pronounce that correctly. I remember like it was on the right hand side of the page and where it was in the physics book, and reading about what that was. That in this case it was, I think it was electrons traveling faster than the speed of light in their medium. Is that right? No, the photons traveling faster than the speed of light in their medium. Anyway, these accelerated electrons gave off this blue photon that you know you don't normally get to see, right? They knock it off and they use green in the Simpsons cartoon, right? You see this green. But I thought to myself when I read about them, I'll probably never see this in my whole life. Like I'll read about it here, and I'll never be exposed to. And it was my first year in grad school. I'm at the Missouri University Research Reactor visiting, doing a neutron diffraction experiment, and I asked I asked we kind of made fun of him because he was bald, that he's working with radiation, that's why he's bald. But, obviously that wasn't the case. But we were joking around with him and said, well, can we see the reactor? And because everybody's working on instruments that are way outside the reactor, in the different experimental. And he's like, nobody ever asks to see the reactor. Of course you can see it. I'm excited. It was like, he was surprised that we even cared. And so we went through this special radiation detector and everything, went into this room, went to the control room with all the panels, just like you see in the movies for a nuclear reactor. And there was a little chain at this kind of mezzanine over the reactor, over the cooling tower. And you could walk right up to it and lean over and look down in the water, and there it was, this blue glow right there at the bottom of the reactor. And maybe events like that was one of many events in my life where I thought this would never happen to me, and it did happen. And it snowballed from there. I've had so many chances to work with great people, get to go see things I never thought I'd get to see, and believe that it's possible. So by now, of course, I'm going to try and achieve what other people might say is impossible, because it is.
Yeah, it kind of gives you a feel that anything's possible. You can see it, you can go do it yourself, you can go achieve it. That's really fascinating.
That's great. Well, thanks again, Jay. This is super, super fun conversation. Love learning more about it. I would want to definitely have you back on and talk more about this stuff. I think we could just keep going.
yeah, we didn't talk much about Mars. We didn't talk much
But
about all of that. Uh, I would love
yeah,
to go there personally myself. That's on
you
my,
want you're signing up.
well, I
You'll
think
be
maybe I back down to like, let's do the moon first so that I can come home, because I'm not so sure if I went to Mars I get to come back. But it
But
would
they
be.
send people out there so that you have motivation to figure out how to come back.
That's
That's how it works.
But
right.
anyway, yeah, no, it's all these, like, you think it's impossible, then you go try it, and then you get to do it. It's I hope I'm right, right? I mean, we're still on the precipice of many things that other people said were impossible. So we have to be a little bit optimistic to keep trying and get over those humps that are before us.
Yeah, it's kind of I mean, I guess you get a little bit used to it, but it's sort of it's kind of an uncomfortable place to be, right? You don't have the assurance that that's going to work out, might not, right? So it feels you have to be a little bit tuned for some adventure and some stress at the same time.
Yeah, yeah. The broken record that I tell a lot of my students or employees is, if it was easy, somebody else would have already done it.
Yeah, no, I think that's so true. I think it's so true. Yeah,
Yeah,
things aren't always easy. I'll
I've
take easy.
enjoyed, yeah, I've enjoyed getting to share this with you guys too. Um, I know you've been there through most of it. You've seen it all happen. So
Yeah,
I,
no, I will never forget now that first conversation where I think it was like a month after you'd started. It was like 2.5 hours. I'm like, okay, you got a bunch of ideas. Let's just like get them all out. Let's go. I mean, it was like 2 or 3 months after you started, but and I remember I probably still have the page somewhere where I was just taking notes. And this bottle cap idea was one of like, 50 things or whatever. And I'm like, oh, that I can see how that could be a big deal. Tell me more about that, right? And then it started to grow from there, right? I think you pretty quickly reached out and chatted with Alex and some of his team and kind of got, you know, building out the idea with them. And then the OSU sort of student team did some work, and then you just started solving problems. And I started bugging you about timelines. And then eventually people started bugging you about budgets. And then
Business pressure we were referencing.
yeah, exactly. And then people started to see the light and they stopped bugging you about budgets and then but they started bugging you more about timelines. So that's kind of how it goes. But yeah, I'll never forget sort of where, I remember those early conversations where it's like, oh, this could be a big deal.
it still seems like one of many big deals to me, but right now it's the big deal that we got to go execute on. But I'm looking forward to getting back to that list.
Yeah, me too. I think it's probably grown. I keep hearing about new stuff, new PETF possibilities and things that we can do. So I'm excited to sort of map that out further. I know people even today were talking about the product roadmap, so that'll be fun.
Well, thanks.